there. So if it's greater than 1, it looks like that. That's called growth. If b is between 0 and 1, we have a graph that looks like this. That's called decay. So basically coming into this, that's what I would hope that you would know. Or at least I'm reminding you of, and you're like, oh yeah, I remember that. Okay, now a couple things that I'm not for sure if anyone has talked to you about is what happens if we have things that don't meet those requirements. What happens if b equals 1? Then it'd just be 1. Well, that's no fun. If b equals 1, 1 to the x power is always 1. So that's why we throw that number out. It's not that it's impossible to be that. It's just, that's boring. It doesn't do anything. It's not really exponential. We don't have growth or decay. We have a line. Same thing with 0. What happens with 0? 0. We get a line right there. So again, that's boring. Both of these are linear. So they're not exponential. They're just linear. So they don't fit the model that we want. Now, the fun one is whenever b is less than 0. Okay. So let's just take one for an example. Let's just do something like -2. Okay, what's -2 to a 0 power? 1. Oh yeah, this isn't totally linear. It has a bump up right there. So it is a little messed up. Although you could argue that because 0 to the 0 power, anything to the 0 power is 1, but can you really take 0 to the 0 power and get 1? That one's kind of yeah, that one's a little messed up. Everything to 0 power equals 1, but you're saying you can take 0 and multiply it by something and get 1. Okay, but that question aside, let's go back to this. All right, so -2 to the 1 power, what's that going to be? Yeah. What's -2 to the 1 power? -2, so it's down here someplace. Okay, what's -2 squared? 4. Well, what's -2 cubed? -8. -2 to the 4th. So you would think that we start having a zigzag, right? Well, no, we don't have a zigzag because we can't take -2 to a power and get 0, can we? And in fact, what's -2 to the 1/2 power? No, that doesn't exist because that's the square root. But I can take -2 to the 1/3 power because the cube root of -2 does exist. So I do actually have a point at 1/3. So what you get is you get a bunch of random dots that bounce back and forth up and down. Negative powers exist also because negative powers are just fractions, right? So negative powers would do the same. They would just be bouncing back and forth closer and closer to 0. So I get a whole bunch of dots that are bouncing back and forth closer and closer to 0. That's why we don't deal with the negatives. It's a cool thing to look at and think about, but not so fun to actually use. Actually, it's not that much fun to think about, and yeah, yeah, fun is relative. Okay, so that's why whenever we do these, we restrict them to this. I don't know if anyone has ever told you why we restrict it to those, but that's why. A lot of times they just say, oh, we restrict them to this, and they move on. That's why we restrict them. It's not just to be mean. There is a purpose to it.
Wait, why is it bad to have them bouncing up and down?
Well, it's not connected at all. Every point that you would give me, I can find a point next to it that doesn't exist. So it's not connected. And plus, I mean, every point that next to it not only doesn't exist, but I can find a point next to that that is negative if you gave me a positive one. So it doesn't work for anything. We want functions that we can actually use to explain things. That's not going to explain anything. I mean, we can use a growth model to explain stuff in real life. We can use a decay model to explain stuff in real life. What in real life is this going to explain? It would be cool if it explained something, but I mean, you can make it your life goal to find something that this will explain, but good luck with that. Dark matter. I mean, yeah, Sean's emotions. You know, I could get really, sexist and say women, or now that's recorded. I just got really dirty looks. So, whenever I'm fired on Monday now, okay, so this now explains my job. One day it exists, the next day it doesn't. Yeah, I know, yeah. Okay, now the general function. What? Quit before they fire. No thanks. Probably not, no. It's a government job. I don't get anything. No, we don't even get that anymore. We used to, after 10 years of work, they would give us like a keychain. They stopped doing that. The keychains were too expensive. We don't get keychains anymore. We don't even get the piece of paper that came along with the keychain because that's too expensive. Now we get announced. They can still afford the announcement. Okay. There's your general function. It should look familiar with the A, H, and K stuff. So again, we're going to use all of our junk that we've been using. A, we're not going to really use that as slope because that's not going to work too well with our exponentials. What we do use the A for is mainly with flipping it upside down. If A is negative, then that is what flips us over the axis. So, we have a sad face that had a stroke now. There's no reason to fire me. H still shifts you sideways. K still shifts you up and down. K is actually going to have a lot more importance on this one because these have asymptotes. So your asymptote is actually going to be equal to K. You have a horizontal asymptote. Since our graph goes like this, it follows a horizontal asymptote right here. So since K shifts you up and down, it takes that horizontal asymptote and it shifts that horizontal asymptote up and down. Well, your original horizontal asymptote is at y equals 0. So whenever you shift that up and down, that's going to be equal to K. So if you shift your graph up 3, then your new horizontal asymptote is going to be at y equals 3. So I'll show you all that whenever we get to the graphing. All right, am I good to switch? I need to get a drink, so if you want to grab graph paper, go ahead and grab graph paper.
Thanks, bro.
I still haven't paid people back. Years ago.
No, my brother.
Yeah, bro, you sold me $7, bro.
Oh, that's true.
My brother.
I probably won't pay you back. Thank you for
You
the
still
charity.
owe me.
That was from like.
That's the perfect reason to loan him more money.
Yeah, just actually, this is your opportunity to get me to owe you more.
You need to keep loaning him until once you reach an even 100, then he'll pay you back, I'm sure.
Just give me one big bill.
Actually, if you lower it, I'll pay you back. Set up a payment plan. I'll pay a certain amount every
2 pennies every day.
Tell him that you're willing to set up a payment plan as long as he's willing to pay interest.
Oh,
I'm not willing to.
pretty good.
Since when are you the negotiator of this?
As long as I get a cut.
You're always in it for the cut. We're always
I'm a teacher. I have to find ways to make more money.
left you at the last time, and I didn't let you at this time.
Okay, you guys ready? All right. So I wanted to start off with a couple basic ones just to get it set up on how we do the graphs. Exponentials do have an asymptote. The asymptote runs on the base graphs along at 0. Okay, if I just plot a few points, if I plug in 0, what's 2 to the 0 power? 1. Okay, what's 2 to the 1 power? 2. What's 2 squared? Okay, if I go the other way, what's 2 to the negative 1? 1/2. Okay, what's 2 to the negative 2? 1/4. Okay, so there would be your exponential graph. Yeah. Y is asymptote 0? Okay. Is there any exponent I can raise 2 to get 0? So, here's the question. 2 to the what power equals 0? There isn't one. Because, I mean, there definitely isn't a positive one. 2 to the 0 power equals 1. These negatives just flip it over. So whenever you're doing a negative, it flips it over, but this bottom number keeps getting bigger, which makes it smaller, but it's never going to turn it into 0, because to turn it into 0, the top number has to be 0. Well, the top number is always 1. So there is no way to make it equal to 0. So you're never going to cross that line. So that's why there's an asymptote at 0, because there's no way we're ever going to cross that. There's no way with an exponent to ever change that sign. That exponent will never change this 2 into a negative number. Because again, a negative exponent flips it over, but it never changes the sign of the number.
Wait, how did you get 1 or 0?
2 to the 0 power. Anything to the 0 power equals 1.
0,
Okay, with 1/2, it works about the same way. 1/2 to the 0 would be 1. But this one kind of goes backwards, because what's 1/2 to the 1 power? 1/2. 1/2 squared would be 1/4. Now, whenever I do the negative power with 1/2, it flips it over. So 1/2 to the negative 1 is going to be what? 2. Because if I take 1/2 and I flip it over, I'll get 2. So if I take 1/2 to the negative 2 power, I would flip it over and then square it. So what would I get? 4. Okay, so that's what all your functions should look like basically. You should either have a growth function or a decay function. Okay, example A, I put a negative in front of it so you could see what that would look like. Now, the negative doesn't change our asymptote. The only thing that changes our asymptote would be a k value. Okay, but if I put a 0 in here, I still get 1, correct? But then I take that 1 and I take it times a negative. So that would give me negative 1. Okay, I take 3 to the 1 power, which is 3, and then I make it negative. Okay, if I square it, 3 squared is 9, and then I make it negative. Okay, going the other way, I'd have 1/3 and 1/9. So again, all the negative sign in front of it does is flip it over your x-axis. Okay, before we even start, what do you think number 4 is going to look like? Exactly. It's number 2 flipped. It looks like number 2 flipped over the y-axis. A lot of your problems are not going to look like this. they're going to look like this. Because if I put a negative exponent on this, what that means is it means this. So I could have rewritten this one like this. It would have been the exact same thing. So this one means this. Oops. But sometimes they show it by putting the negative on the x, because the negative exponent just means you flip over your number. So go ahead and graph that one real quick. And you should have something that looks like that. Okay, let's do something with H and K. Okay, my K is 4. My asymptote was at 0. K takes everything on my graph and shifts it up 4. That includes the asymptote. So if my asymptote was right here at 0, that means I have to shift my asymptote up 4 units also. So 1, 2, 3, 4. So here's my asymptote now. Now, you can choose to do this however you want. I'm going to kind of show you how I do it. If you want to just plug in points, plug in x values and graph, go for it. I'm going to show you how to get the proper x values to plug in because that's very important. Otherwise, you're going to get some huge numbers. But I'm going to show you kind of how I do it. All right. What's my h value? Close. 3. So that means I'm going to shift over 3. 1, 2, 3. So right here is the center of my graph. Now at the center of your graph, how far up should you be? From your asymptote, you should be up 1 point. So what I do is I just graph off of my asymptote. I should be up 1 point from my asymptote. Look at your past graphs. How far from above your asymptote are you